first colloquium of 2023 of the physics department. We usually hold it on Wednesday, and unfortunately we are delayed by some time due to unavoidable circumstances, and it's a great pleasure to have with us Professor Arindam Kundagrami from IISER Kolkata. A formal brief introduction of the speaker is needed. I see that Professor Kundagrami graduated from Presidency College, actually, Capital University. That was in 1994. And then he did his MS specialization in theoretical condensed matter physics from IISER, Bangalore. And got his PhD from the University of Pennsylvania in 2003. Then he spent some postdoctoral years at the University of Massachusetts till 2010. And from 2010 he is at IISER Kolkata, currently an associate professor there. And he has a very broad research interest, very interesting field of work actually. For example, he is interested in equilibrium statistical mechanics of polyelectrolytes. For example, ionizable polymers or gels, such as dynamics of phase transitions. Phase transitions as such, topological defects and chiral segregation of liquid crystals. These are some of his research interests, and we are all eager to know from him something about soft condensed matter physics, a few basic principles. Professor Kundagrami, please.
Thank you, Professor Raychaudhuri.
Yes, listen.
So, thank you, Professor Acharya, Krishna, and all of you for inviting me. This is my own place. I used to be that side sitting here. Possibly for the first time I'm doing any lecture in the college. So even including that time. So very pleasant. I will be talking about some basic concepts, the way I understand about soft condensed matter physics. So to start with, we know that traditionally in Indian universities, the way condensed matter physics is taught is the so-called hard condensed matter physics. The first course of condensed matter physics is taught that way. So what is done after the statistical mechanics course, the preliminary basic equilibrium statistical mechanics course, people start, the standard books like Kittel and Ashok Warming, in which one studies the Fermi electron gas and phonons, things like that. I want to present soft condensed matter physics in a way that it is basically an extension of statistical mechanics. So it's basically application of statistical mechanics, nothing else, but to the so-called classical systems, in which the constituent particles, they do not need quantum treatment. So basically, one can, if one does simulation, the particles can follow Newton's law instead of Schrödinger's equation. So that is where, but before going into that, I'll very quickly go through just a very brief introduction. So as you know, that in classical mechanics, you look at the position, velocity, energy, and classical model, such as the near ball. This is Newton's law, and then special theory of relativity, and the particle moves very fast. But still classical. And then quantum mechanics, position, velocity, energy, slow moving quantum particle, and then quantum relativistic quantum mechanics, quantum electrodynamics. All these are single particle physics. But then this is not all, because we have charge in our nature. Charge is not analyzable in terms of space and time. It's not a mechanical quantity as such, and the force generated by charges are different from force generated by mass. So we have Coulomb's law, although they are very similar in nature, the dependency of distance. So that is electrostatics. But these are not fine for single particle physics. If you look at your course curriculum in physics department, you will see that the courses are structured in that way. But what happens when you have collection of particles? All these particles are either following Newton's law or Schrödinger's equation or Klein-Bott equation, relativistic quantum mechanics, whichever way, but collectively what do they do? One can in principle solve Newton's law for all of them, 10 to the power 23 particles. Well, in principle possibly that is not solved, so many particles. Even if you can do that, solve solving of stuff, all of them, still it might not be useful, because what do you do with all those equations? So it is, you have to get to the bulk properties of the system. How do collectively the particles behave? So that is why, and this is not new, that is why originally thermodynamics started. So thermodynamics was an empirical subject in some sense, very complicated. Thermodynamics is the most challenging subject in physics which I have read. It's fantastic, it has lots of details, nuances. But thermodynamics, what they did, in which in thermodynamics people studied the temperature dependence of several systems. It can be gas, mostly gas, fluids, like Reynolds fluids, and in some cases solids, not exactly thermodynamics, but when you are thinking of solids, the first thing we will study possibly elasticity, right? The extensibility of a solid, because it wants to come back, just some rigidity. So those are sort of bulk properties. Elasticity is a bulk property. You cannot think of one particle and think of elasticity. Thermodynamics, hydrodynamics, things like that. You need collectively. So the first thing that comes about after thermodynamics, people started thinking about that what is the origin of the properties which we observe. What is the microscopic basis of that? Is there any? And surprisingly, even late 1880, 1890, late 19th century, right? Even at that time, people are not aware about the atomistic nature of matter. There were still controversies, right? So, because if you have to go to the microscope, you need to know about the atomistic nature of matter. So once that was understood by people, and it took a lot of time actually. We initially started with the kinetic theory of gases. So people wanted to know what is the pressure. Pressure is some force applied by a confined gas. So that force, that pressure, that had actually some statistical origin. Because one single particle doesn't constitute force or pressure. You need collective behavior. So initially the kinetic theory of gases, the original theory, that came. But that was still not statistical mechanism, because kinetic theory of gases by name is for gases only. So where do you get a theory which would apply to all possible thermalized matter? That means system even beyond thermalized matter nowadays, but at least to start with matter where the molecules they respond to temperature, respond to heat. So that was the initial query to get a common theoretical formalism, and that is where statistical mechanics came up. Now let me go to soft matter. See, most of you know about statistical mechanics as well. How do you think about the ensembles, the microcanonical ensemble, canonical ensemble, grand canonical ensemble, where you think about collection of particles with constant volume, energy, number of particles, fixed temperature, things like that. It depends on which ensemble you are looking at. Then the soft matter, as I have already told you, it's actually application of that statistical mechanism to collection of particles which respond to external forces at normal temperatures, close to room temperature. So if we look at condensed matter physics, it's mostly about looking at responses to external forces. Forces or fields, right? If it is response to external forces, for example in a gas, we look for compressibility, because you apply some pressure, how much the volume changes, right? Compressibility. Or you apply a magnetic field, external magnetic field, how much does the magnetization change? So these are the response functions. So whenever people look at a condensed matter system, they look at the response function and what is the response at particular temperature. For soft matter systems, responses are perceptible, nicely observable at room temperatures. That is why at room temperature, entropy is a very important quantity for soft matter systems. Now what are the examples you can think of? So the four big pillars, four big types of materials for soft matter, they are called liquid crystals, colloids, polymers and membranes. Membranes have some liquid crystals, but these are the major things. But if you think about colloids, for example, milk is a colloid, as we know, most of us know, that, for example, the milk particles, they are like fat particles. They are of size of micron. It's a micron-sized particle, and because it's a micron-sized particle, you really don't need to apply quantum mechanics for that. There can be a collection of particles suspended in water, exactly what happens from milk, and it will scatter white light because the particular wavelengths you have in white light, visible wavelength range, the fat particle size is compared to that, and that is when you can scatter white light. That's why milk looks white, cloud looks white. That's the reason, right? So that is one example. Then you have like foam, paste, rubber, body muscles, anything that is soft to touch in that sense, and it responds to normal simple forces. But again, finally, it is a collection of particles, and broadly they can be classified in these four categories. Now, as I have all of fluid physics in some sense, but simple fluids are not sweet twisted. For example, water. Water is on its own. Water is enormous. Several huge number of scientists work on water, different properties of water, and water is not only a fluid. We all know, right? It's not as simple as other, but it's ubiquitous. It's everywhere. But simple water, because water does not resist shear at all, right? So it's a pure fluid, it's a liquid, it's and you can think of crystals which will resist shear, okay, to a certain extent. Now you can have materials which are in between, which will resist shear to some extent. So sort of viscoelastic, right? So those kind of fluids are more interesting as long as we are in the realm of soft matter physics. So although I write down fluid physics, generally we'll think about those fluids. For example, polymer solution. It is also a fluid, but its elastic properties will be quite different from water. Okay. Liquid crystals, in which the isotropic shape of the molecules that will generate order. I'll show you shortly. That will generate order, which is in between a perfect crystal and a liquid. Okay. Then colloids, which emulsions, microemulsions, nicer vesicles, membranes, and writing all of them within colloids, but well, then there are mixtures, right? Like liquid crystals, depending on the shape of the molecules, they will form different types of membranes and all, and then finally you have polymers, in which, for example, nanometer size monomers, nanometer size particles, they will get connected. The organic molecules, they will get connected, and they will form a very long chain. And that chain, because of the connectivity, that chain will have very interesting statistical properties. Many of you know about the random walk, right? Random walk. So a polymer can be created by the random walk of the monomers. But that's not all, because when you are doing a random walk, a reverse step can be taken in the opposite direction. But for a polymer, actually, you cannot do that because two monomers cannot occupy the same position. So there are differences. We'll come to that later if we have time. Now, as we have already discussed, what are the basic properties? Thermal fluctuations at room temperature. I'll soon describe what this page is. Thermal fluctuation at room temperature, introductions of modern KBT. That's what we should do. So, KBT, that is how people say that the system is thermalized or being thermalized, or the system is susceptible to be thermalized if the interaction energy in the system is of order KBT, where T is the room temperature, right? Or the temperature equality. It doesn't have to be room temperature exactly, but somewhere between for the temperature for which water is liquid. So 0 to 100 degree, we can think of that those systems in soft matter systems, but mostly room temperature. Most soft matter experiments are done at room temperature. Okay. So easy versatile response to external forces. Importance of fluctuations due to Brownian motion, right? Most of the particles they will be doing Brownian motion depending on their size, and their movement will be restricted depending on their size and the viscosity in the liquid, right? And all possible is it is possible to have a two-dimensional crystal but a one-dimensional liquid in the same system. Okay. That is why it's called liquid crystal. No order like a liquid, no order like a crystal. Come back to that. Ordered phases respond well to external forces like pressure or magnetic field. Magnetic field is not a force but an external entity against which the magnetization changes, right? And entropy plays a huge role. Now, I'll very quickly go. I have already talked about it. There are theories for collective a collection of particles, bound properties of matter. The kinetic theory and thermodynamics and statistical mechanics 10, which is still the most popular theory. Statistical mechanics is everywhere in quantum physics, right? Observable variables. Now, try to think about which systems will be applied to. Particle density, momentum density, magnetization, spin systems, right? Some of you know about IISER, charge density. Of course, if there is particle density, if the system is charged, there will be charge density. Response to external fields like compressibility, susceptibility, elasticity, periodicity, that is mostly in particle density, and magnetization. So, I have already done magnetization. So, these are the observable variables, examples of properties, some properties which you have already discussed. Liquid flow condition, doesn't resist. Solids are rigid. Gases take the volume of the confinement, but the liquid will not. Right? Liquid will flow, but it is almost incompressible, almost like a solid. Most liquids in normal temperatures, for example, water is incompressible. Now, just like any other condensed matter system, how do you approach the problem? To solve the problem, that means you have a collection of particles, you want to know about the phases. Will it be liquid-like? Will it be a crystal? Will it be gaseous? Or if it has spins in the system, magnetization, what will be the magnetization? At what temperature? If you have to answer these questions, first you have to understand the interaction. It is true for any condensed matter system. You need to know what the interaction is. Why? Because then you will write the Hamiltonian. Once you have the interaction, you know the energy. Energy goes to the Hamiltonian. Not exactly, but if you have the idea about the energy, you can write the Hamiltonian and partition function. Partition function will take care of the entropy. Yeah, right? I hope most of you will be familiar with that. And then from partition function, if you know the canonical ensemble, you can get the free energy. I'll go in slightly more details with proper equations very soon. And then the free energy will be a function of particle charge density magnetization. The quantities you want to observe must be there in the free energy. And then or must be derivable from the free energy. Not necessarily in the free energy, must be derivable. Pressure is not necessarily part of the free energy for the liquid gas system. For example, vapor water and liquid water, if you are thinking about the van der Waals gas water as a van der Waals fluid, in that case, the canonical free energy will not have pressure. Pressure has to be derived, right? But should be derivable from the free energy. I'm talking about the statistical mechanics formalism. There may be a different thermodynamic formalism for that. But for now, whatever we will do, follow statistical mechanics. And then you do the analysis of equilibrium. Now, very quickly, let us go through a basic example. 3 states of water. And what are the variables? What are the things we look at to develop the notion of condensed matter physics in general? Soft matter physics in particular, but in general, these are all applicable to general condensed matter physics, including hot condensed matter. So, high temperature is disordered, uncoordinated, uniform, isotropic. All these words have very specific meaning. Disordered, that means there must be some order parameter based on which I am saying that this is disordered. Okay. Gas phase is disordered, the liquid phase is also disordered, but the solid phase is not disordered. Solid phase is ordered. So you have to think what is different between the fluid phase and the solid phase. So you have to define order in terms of that particular quantity. I'll come to that one. Okay. Then uncorrelated. Uncorrelated means So, if you have one particle at a preferred location, can you predict the position of another particle? If you can predict, then the system is correlated. If you cannot predict, the system is not correlated. Gaseous system is not correlated. If you know the position of this particle, you really don't know where other particles can be. So that's why we say equal probability of finding a particle at a point. Equal probability because they are moving all the time. And you can think about the microstates in terms of position only. In the positional phase space, the microstates, right? Positional phase space microstates means different snapshots with different positions of these particles. And they are equally probable everywhere. That is why equal probability of finding a particle at a point, and that probability is independent of the presence of other particles. Of course, because they are so far from each other. Liquid is the most interesting. Welcome to the full rotation of the translational symmetry. What does it mean? If you rotate the system, suppose this is the room full of these molecules, spherical molecules, and if you rotate yourself or rotate the system, the system looks the same. It actually doesn't change. Okay, it will change from the solid. You know, compressible gas is compressible, but liquid will not. Compressible because if gas is compressible, we know. Well, you have to. It's far more compressible than a liquid. And energy, internal energy. Now you have to think about on what quantities internal energy will depend. It will depend on the interaction potentials. The particles are so far apart and they are not charged to start with. Uncharged dipolar interactions, they die down very quickly, so the gas particles basically do not interact with each other. You know the kinetic theory of gases, the entire theory is derived considering there is no interaction among the particles. Okay, so energy is not very important. Entropy determines everything. Entropy is maximized, and that is the equilibrium. Okay. Go to liquid phase. Still disordered. Again, think about what is the order point. And better correlation. What is better correlation will come to that uniform. Uniform, it was the isotropic. So uniform, isotropic, disorder. All these are comparable to the gas. But a gas and a liquid, they are so different. How are they different? They are different because liquid is incompressible. And what is the result of that? Incompressible, high density, doesn't resist shear, gas also doesn't resist shear. Rotational translation symmetry is there for the gas also. But look here, if there is a particle, this is a liquid, if there is a particle at a preferred position, there is a good chance that another particle is one diameter away. There is a good chance. Not like 100% chance, like a crystal, but there is a good chance. 2 diameters away, still a good chance. There is no particle 1.5 diameters away, no particle. Good chance. But 5 diameter away, no. You are now unsure. You really do not know because it's not like a crystal. You really do not know whether it is 5 diameter away because they are not ordered like a crystal. So the correlation dies down within a few diameters, within a few molecular diameter distance. So that's why they call it short range correlation. This is the result of or they are connected with incompressibility. They are so close to each other, well packed. Okay. So E is comparable to entropy. So entropy is there, it's moving around. Right? The particles are not fixed like this. Remember, this is just one snapshot, one microstate. There are many other microstates, billions, zillions, almost innumerable number of microstates, for which the positions will be different and the velocities also will be different if you think in terms of bases. So what happens in a solid? Now see the difference. Solid is ordered, and in Condensed matter, more symmetry means less order. That is when I read it for the first time, I got a little bit confused. By order and symmetry sometimes connect to each other. Greater order, more order, crystal, less symmetry. That means symmetry is broken. This system, you rotate, don't think of the system only confined by this. It's a thermodynamic system. It is infinite. Imagine you are inside the system and you have infinite number of such spherical particles. Then you rotate the system you move inside the system to some extent, system looks the same, translational invariance. If you rotate the system, translational invariance. But look at the crystal. The crystal, if you are here, you are middle of the particle. You are just in the center of the particle. If you are here, you are at the junction of two particles. So if you move by half a diameter, you look at a different system. And that is, one more important thing is, in the crystal, the molecules, they stay almost at the same location. They vibrate. They vibrate with respect to an average position. But the liquid, they don't do that. They move around. So when you take an average, so when I say system looks the same, it is over many snapshots. Because if you think about only this snapshot, then system will of course look different if you go from here to there. But remember, these molecules are moving. These molecules are only vibrating. That's the difference. So if you are standing somewhere, you can clearly say, am I standing on the lattice point like here, or am I standing an off lattice point? It is clearly you can identify the crystal. So this is more order, less symmetry. Why? You rotate the system looks different. Because the positions are fixed. You rotate the system, this system by in this case 180 degrees, it will look the same. So rotational symmetry, now I have discrete rotational symmetry. I don't have continuous rotational symmetry. Symmetry is broken. As soon as the symmetry is broken, rigidity will come in the system. I'll come to that. So these are related. If symmetry is broken, continuous symmetry is broken, there will be rigidity in the system. So this is rigid. Like this is not a crystal, but think about an iron slab or an ice crystal. If you put shear, there can be shear melting, but it will not move. But if you put shear on water, right, you put on the surface of the water flows. So this is water. So this is water, liquid water, and this is ice. Now, we have discussed this, and very quickly I'll tell you about this air correlation function, how to calculate it. We have mentioned this statement, right? If there is a particle at a particular location, what is the probability of getting another particle at a particular distance? The way it is calculated is very simple. You choose a particle, choose that to the origin, you draw a spherical shell, this is R and this is R plus dr. So the spherical shell is 4 pi r squared dr. Within that 4 pi r squared dr, how many centers of the particles will fall? You count that, divide by the volume, that is how it is calculated. Calculation is very simple. If you are doing a simulation, you can very quickly calculate that. And probabilistically you can see that this quantity beyond a certain distance will be constant for a fluid. Now how does it look for whatever I have shown you there, going a little bit fast because I want to finish a few things. So you can stop me anytime. Anytime you have a question, you can stop me. So how does that quantity which I have just described, how does it look for a gas, liquid, and a solid? For a gas, there is no particle. If you have a particle at origin, there is no particle within one diameter distance because there is a hard-sphere function. But the probability of having another particle is constant. One is a questionable thing. There is a normalized shear of R. It cannot be 1, right? The overall probability sum over should be 1. Okay, of getting one particle. So it is constant for a gas. For a liquid, remember we discussed one particle distance, high probability. 1.5 particle distance, no probability. Like a crystal. 2 particle distance, reasonable probability, but not as high as that. So we are losing correlation as we are going away from the center of the source, main part.
Sir, if we think about amorphous solid, then also the long range order cannot
take. Not there. Amorphous solid is like liquid.
Yes.
Yeah. Yes.
So can we treat that soft matter, that amorphous solid?
Yes, people do, like glasses, right? Glass people do. Those are slightly special materials, and of course, you are right. Amorphous solid. But for a crystal, for an if you know there is one particle at the origin, you definitely know one particle at one diameter distance, 4 diameter distance, this doesn't go down. Ideally, in practice this doesn't happen because the crystal will have defects. Right? But still, in principle for a liquid, this will go down. In principle for a solid, crystal, not amorphous, it will not go down. If there is a particle at the origin, you know 500 million crystal diameter distance away, you will find another particle. But million 0.5 will not find one particle, right? So it's like, but actually it doesn't happen. The motivation dies down because of the defects in the crystal. But it is definitely much more ordered than the solid than the liquid. Now, as we have talked about this broken symmetry and rigidity, how they are related, you can think about these two atoms in a crystalline solid, atoms or molecules. So this distance is actually A. I have drawn it just to illustrate it. I have drawn it slightly separated. And this is the ideal equilibrium distance. Now you increase the distance by some force. It will try, this displaced molecule will try to come back. It wants to come back. So that is elasticity. Now what will be the strain? Strain is x by A by definition. What is the stress? If G is the modulus of elasticity modulus, and Gx by A is the stress because G is stress by strain, right? So the total force, so if this is the stress is pressure per unit area, total force, it's a very rough calculation, very approximate calculation, but it will give you some idea. So this is A, so I can assume the force is acting on a surface which is of order A square, okay? Because if the lattice spacing is A, the force on a particular molecule is acting on a surface of order A square. So the total force is stress into area, that is right, that is equal to Kx, which is K is the, so this is the force, Kx is the restoring force, just like the elastic spring. Now you can see from these two that K is Ga. Now we go to the equipartition. This is the basic definition of elasticity. You go to the equipartition theorem, you can see that average potential energy which is K half Kx square for the spring, so for those particles, harmonic oscillator. And kinetic energy is half kT for one dimension. If you compare that, you can do this calculation in the half order type mode. If you are not liking the equation sign, you can give the half order signs as well. So from here you can see that average, so displacement square, displacement can happen in both either directions. It's kVt by K, so kVt by Ga, this is the elastic modulus. So the average displacement square, modulus displacement, that increases with temperature. So vibration increases with temperature. And the vibration will be less if the elasticity is higher. The elastic modulus is higher. Okay? So you can see already from this simple calculation that temperature, thermalization will try to destroy the order and elasticity will try to restore it. This is the order destroyed phase, liquid phase, where the elasticity, the shear elasticity which we are talking about, that is lost. Compressibility, the bulk modulus is still very high for liquid. I am not talking about that one. I am talking about the shear resistance in this case. That one. And for crystal, you can see the rigidity maintains the order, and the symmetry is broken here, symmetry is intact here. Symmetry is the rotational and the translational symmetry. So you can see rigidity is necessary for periodicity. It will remain periodic with the rigidity. To remain periodic, that average x square should be less. If it is too much, if it is vibrating too much, it has become a liquid. That means the melting has occurred. Okay? So for rigidity, to maintain periodicity, to keep this quantity low, I need rigidity, that means high, relatively, depending on the system, depending on the temperature, high elastic particles. Now another concept, non-wavelength fluctuation. What is a non-wavelength fluctuation? You can think of the spins. Spins in a ferromagnet, as in model you can think of a ferromagnet. All the spins which are aligning, pointing to a particular direction. So they are ordered. So what can happen? And these are the lattice points. What can happen? That in the consecutive lattice points, the spin is having an angle. Remember, these two are equivalent pictures. For a crystal, this is the equilibrium distance. If the molecules are separated by this distance, there is no elastic energy. There is no elastic energy cost. Likewise, if these spins are parallel to each other, there is no elastic energy cost. The spins have an angle between them, then there is an elastic energy cost. If this distance is larger than this or can be smaller than this as well, but because remember, this is not exactly a hard sphere. There is an electron cloud. The electron cloud can be pressed against each other, can be taken far from each other both. So can go either way. But if there is a deviation from this equilibrium distance, there is an energy cost. So these two things are equivalent. A divergence between two spins and the distance between two molecules, which is not the ideal equilibrium distance. These are equivalent in terms of generalized elasticity. Both of them will have elastic costs. So what can happen? There can be small rotations for the spins. It's a one-dimensional system. And you can see there is a pi by 2 phase change, or angle change. At 1, 2, 3, 4, 5 lattice spacing, 10 lattice spacing, 5, 15. In 20 lattice spacing, it comes back to its original direction. Okay, so this is called a long wavelength fluctuation because you can see that in many lattice spacings, in a large distance, in units of the lattice spacing in the system, the phase of the, so this is, I have told you this is the, you can think of this as the order parameter. The phase of the order parameter changes. In this case, what happens? You can see there can be a small deviation, small separation here, another small separation, and all these small separations in 1, 2, 3, 4, 5, 6 lattice spacings will add up to give one lattice spacing difference. So this is an equivalent small wavelength fluctuation. What I wish to tell you, remember crystal is ordered. Crystal has order, less symmetry. Liquid has less order but more symmetry. Then what is the order parameter? The order parameter between the liquid and crystal phase transition, that order parameter is actually the periodic mass density. So this is the mass density wave, or the periodicity intensity that is there for the solid, but it is absent for the liquid, right? In the liquid, if you are looking at positions, if you are looking at positions at equal intervals, we will not get the same mass density. We will get that for the crystal. So that's the difference. And in this case, you can see we are assigning a phase angle 0 to this, phase angle again 0 or 2 pi here. So depending on the angle of the spin, the phase will be assigned to the order parameter. Here also, depending on the position, if the position is here or one diameter away, the phase angle is 0. But if the position is slightly displaced, then the phase angle is not 0. It is something between 0 and 2 pi. So depending how it goes from here to up to this point, within this distance, all phase angles will be explored for the order parameter of the solid. Okay, this analogy is slightly tricky. You have to think about it a little bit more. We can discuss it later if you want to. Now, another thing which we have discussed, the crystal is not an ideal one. It will have defects. If it has defects, what happens? How do you quantify the defects? We understand the defect means it's not an ideal crystal. But how is it not an ideal crystal? The thing that can happen, look at this. I have 1, 2, 3, 4, 5 atoms. 5 atoms. Now suddenly I have 4, 4. and then I'll have to, and then, so away from this unusual region, away from this, the order will be maintained. But close to this region, you can see there is some distortion. Because, for example, OP, BQ, QA, they all have ideal distance between them. That is so that there is no elastic energy loss. But you come here, IC, CD, EJ, instead of 4, you have only 3 bonds covering almost the same distance. Of course, there will be elastic energy cost. But you can imagine the elastic energy cost will not be extreme. It's like 3 bonds instead of 4. So it is maybe 1.33% or something like that, the bond length of each one of them, and that will cause some amount of energy, but not extreme energy if there is, for this case you can see, so it is almost like long wavelength fluctuation. This is one kind of a defect. You can see there is a phase change of 2 pi if you go around the effect. Suppose you start from here. This is 0, 2 pi, right? Or 0. This is the way you consider the phase. 0, 2 pi. Let us first do this. This is easy. So angle 0. You are going around, or you start from here. 0. This is 90 degree. Pi by 4, pi by 2. Right? Pi by 2, pi. 3 pi by 4, 2 pi, right? So I have 360 degrees. So what is the defect for which the order parameter, the phase, if you go around the defect, the phase of the order parameter changes by 2 pi. And that's not always the case. This is the case for which we call this is a defect of strength 1. There can be defect of strength other strengths. I'm not going into that. So in this case also, 0, 2 pi, 4 pi. In this direction, there is loads of, these are 2 different directions, remember. There is a 1-dimensional system in some sense, the way I have drawn. There is a 2-dimensional system. Okay, so 1, 2, there is no phase change in the x direction here. You come back, so 4 pi, again 2 pi, 2 pi, 2 pi, because y direction, no change in the x direction. So you are coming back with a change in phase of 2 pi. Then you say, within the contour there must be a defect present. So this is the way. So this is called a edge dislocation, just a name of it. This is possibly called the edge hop. You see this for liquid crystals as well. Maybe for the liquid crystal this is called edge. Anyway, I would rather skip this slide because this actually compares different materials for which what is the broken symmetry, what is the new order, rigidity, new modes. We haven't discussed this system. Let me go to the liquid crystal first. Just how much time? 50 minutes. So now, till now, we have been discussing about spherical particles. But not always we have spherical particles. We can have elongated particles. Now, see if you think step by step. I have a spherical particle, and how do I make it anisotropy? What is the least anisotropy I can assign to the particle? Okay, I can elongate it in one direction. I get a rod line. These are called liquid crystal particles. Let's see why. Okay, so rod like liquid crystal. I can compress it in one dimension, one particular direction. So this is a disc-like particle. You know the radius in the x and y direction, they remain the same. This one and that one. The cross section is circular, but this one and that one. This is just compressed, this is elongated. Rod-like, this one. Let's take the rod-like particles. Rod-like particles randomly oriented. This is called isotropy. Think about, whenever you are looking at it, think simultaneously of spherical particles. So if it's a spherical particle, fine. We have drawn it before, like the gas we have drawn. Isotropic, because this has all forms of symmetry. Translationally symmetry, because the centers of masses of these particles, they are liquid-like, they have no correlation. Translationally symmetric, rotationally also symmetric, because they haven't chosen any particular direction. They are randomly oriented. Decrease the temperature, you can get this in matrix phase. how is this important? This still has translational symmetry. Because collapse all these particles to one particles, they are liquid-like or gas. There is no order. But because of this, anisotropy in each molecule, they can actually align along a particular direction. Make them spherical particles will go back to the gas and liquid. But make them elongated in a particular direction. I have some kind of order. This is orientational order. This is not positional order. So you can have orientational order, but no positional order. This is why they call it mixed order systems. Liquid crystal. Because crystal has order, liquid has no order. The system has both order and lack of order. That is why it's called a liquid crystal. It's just that's the name of the nomenclature. It's both a liquid and a crystal. Okay. So then what happens? Then you decrease the temperature even further or compress. Or in case of the lyotropic liquid crystals, you have a solvent which is not liked by the molecules. If the solvent is not liked by the molecules will try to come close to each other. Either way, decreasing the temperature so that the intermolecular interaction is more prominent. Lyotropic solvents for which the particles don't like the solvent but to come close to each other, or you can from externally you can increase the density of these molecules to induce artificial compression in the system. Any of the ways, this is the first phase, then it goes to this phase. You can see there is this is symmetric. It's called one-dimensional crystal. It is crystal in this direction, but it is liquid within the planes. Think about the planes, right? The planes, so there are stacks of molecules, layered structure. See, it's 1D crystal, 2D liquid. Symmetric C is slightly different. Where these are tilted, because it is tilted, it has less symmetry than this. Because the projection of this particular molecule on the this is the z-axis, in the xy plane is 0. The projection of this is not 0. It chooses a particular angle in the xy plane. So this has less symmetry. As soon as it chooses some direction, some angle, some position, there is order, more order, symmetry is gone. Okay? Symmetry is going down. Order is becoming more and more in the system. So that is symmetric C. And then from symmetric A you can have a crystal. Finally, this is a crystal. Within a crystal, there is order in all three directions. So previously I had order in one direction. Now I also have crystalline order within the layers. So it has become a three-dimensional crystal. You can see just because of the anisotropy of these molecules, you have gotten 1, 2, 3 different phases. For the spherical molecules, I only had this and this. So that is why liquid crystals are so important. It will present you with many different types of phases.
So is it just because of introducing the anisotropy?
It is
Or any other
like interactions. There must be interactions. There must be attractive interactions.
No, you have just introduced the anisotropy.
Yes.
You have changed the shape.
Right.
And that's why you are getting this
That's
type
why you are
of
getting
intermediate order.
Yes.
Partial.
Yes. That is the primary reason, but you definitely need attractive interaction between the particles, otherwise they won't come close to each other. If they don't come close to each other, why would they align? Why would they order? They will be like a gas.
So the anisotropy can create some partial order.
Anisotropy is creating partial order. So the anisotropy of the molecules is manifested in the anisotropy in order of the system, bulk order of the system, right? Anisotropy of the molecules is manifested. Bulk order of the system is anisotropy. That means in one direction I have order, in other directions I don't have order. So order becomes anisotropy, bulk order, because of the anisotropy of the single molecules. I'll skip this too because and these are the phases for disk-like molecules. Very similar things happen. You can have two-dimensional crystal, but one-dimensional liquid. Look at this, very nice hexagonal model. This is only a part of it. This is infinite plane. You have to think about. But in this direction, this is liquid like water. That means there is no proper periodicity. They are less conjugated. Okay, so it's a one-dimensional liquid, two-dimensional crystal. Spectrum was one-dimensional crystal, two-dimensional. So many things can happen in a crystal. And then you can have other forms of soft matter like micelles, vesicles. You know how micelles will form. Very quickly I will say this and move on. So this is a hydrophilic end. This is a hydrophilic group. It's in one. There are so many of these molecules. So what they want to do, they want to minimize contact of this part with other molecules. So all these parts will come close to each other. Think of this as a sphere. All these parts will come close to each other. The hydrophobic groups will face the water. Water will be expelled and some spherical structure will be formed out of this diatropic molecules. Okay, so that's one example. Depending on the shape of the molecule, several different kinds of shapes you can generate. And this is one random isotopic factor. And there are many such examples.
Sir?
Yes.
Previously. Sir, from the bilayers it is equivalent to the cell membrane. But the cell membrane is fixed, I suppose. So the order, the particles, as like crystal, the particles are fixed and they are only vibrating. So how can we compare that which is more soft matter or less soft matter?
No,
This is
like that. Yeah, this vibrating depends, right? The crystal will just doesn't move. So, but it moves. The membrane will,
Yeah.
if you press the membrane,
Yes.
it has a response. It has a response to moderate forces. Imagine an iron will have response to unbelievable forces, right? The bending of beam experiment. You need that experiment because iron, that kind of influence. So that's what I wanted to drive home, right? There is nothing called soft matter. All are standard matters, right? It's all condensed matter. Soft matter is just a soft matter term has been assigned to only some subset of materials, but you can see you can possibly seamlessly transit from one type of materials to the other type of materials. Okay? So yeah, how much soft matter, how less soft matter, difficult to say. But cell membrane will definitely respond to moderate forces, which even the ice crystal will not. Right?
yes.
Arindam, for this kind of structure in the micelles, I think the entropy and surface tension play the major role. Otherwise, how can you get this kind of spherical structure?
No, but it will definitely expel water. That is a very important part.
Yes.
Because it is hydrophobic.
So
that is surface tension.
that could be derived, yes.
That is surface tension. See, if you are looking at the molecular level, I am not thinking about surface tension because I can calculate molecular interaction. Surface tension is a result of the molecular interaction.
Yes, gross, yes.
Grossly, yeah. So and other is entropy. Entropy will be important. If you increase the temperature, even with unfavorable contact with water, they will like to explode the entire water. So the micelle will be broken. Micelle will be broken.
But this should be the minimum in entropy configuration.
This is the minimum entropy.
Minimum entropy.
Yes. They are maximizing the interaction free, gaining interaction free energy by expelling the water. By expelling the water and having contact of the hydrophilic groups with water. That is also negative energy. You have to maximize the negative energy. F E minus Ts. F is minimized, E is more and more negative. So, okay. So, very quickly, I believe I have around maybe 5 more minutes. But I just wanted to, so these are all examples. But there must be some formalism. I won't be able to finish all this. There must be some formalism. There must be some quantitative way. In other words, equations to deal with the systems. How do we do that? We have to start from a very basic thing. We started with simple gas, liquid phase crystals. So we should be starting with that as well. Okay. and try to build up a formalism which will be applicable to simple fluids and then will be applicable to complex fluids. You have heard the term complex fluids, right? So, most of the things which we are discussing, complex fluids. Water, simple fluid, but you tell the water scientists, they will be very happy because water is unbelievably popular. I mean, I don't know how many. There are journals dedicated for water, right?
Chemistry.
Chemistry journals, chemistry, physics, yeah, chemical engineers. So, but in our formalism, water is a simple. But in this case, again, we come back to the gas. Think of the gas, but there are two chambers. Traditional old thermodynamics. So there can be particle, volume, energy. First chamber, second chamber, there can be exchange of all of these particle, volume, and energy. Second law of thermodynamics tells you. So I am trying to find first equilibrium, then dynamics candidates. I want to identify the equilibrium in the system. You all know this. Entropy will be maximized, and the way you can write this entropy. Right? If it is maximized, delta should be 0. These are arbitrary. This is delta A. Okay. So these are arbitrary, quantities, differentials. So that tells you at equilibrium for chemical systems, temperature, pressure, and chemical potential should be equal between two chambers, between two phases, liquid and gas coexisting. Temperature should be same, chemical potential should be same, pressure should be same. Right? So coexistence of the liquid and gas. How do you do it? Remember this phase diagram. This is for water, this is the triple point 0 degree, and this is the critical point. Do you know what is the critical point of water? Very high. I don't remember exactly, but 650 degrees Celsius almost. Right? Critical point of water. But what is the critical point? The way we have learned in our school days or even later that critical point is something around the critical, you can go around the critical point without having a phase transition. That is okay, but let us try to analyze this from the very basic thermodynamics and statistical mechanics. At this moment, thermodynamics.
Without having first order phase.
Without having first order. Definitely, without having first order. So this is the line which you are interested in. Liquid gas transition. Okay, and this is 0 degree. This is 640 Celsius. Kelvin. Forget it. Very high. Okay, and this is 0. So 273. And we are somewhere here. 300. Okay. So how do I? My question is, at 300 degree Kelvin, I have a fluid, and it's a single component fluid. That means only one type of molecules. Say water. Only water molecules. Think about a pressure cooker. I have liquid water, I have water vapor. They are coexisting. I'm increasing the temperature. It is not just 300 Kelvin. It can be 350 Kelvin. It can be 380 Kelvin. Okay. 380. Pressure cooker will survive. 373 when water boils. Okay. Pressure cooker still might survive as well. Okay. But let's go to 370 or something like that. So its temperature can be high. So what happens? My question, the first thing we want to know, what are the coexisting densities? At a particular temperature, there will be a particular vapor pressure. Remember, the particular temperature, there will be a particular vapor pressure. The vapor, water vapor on the top of the pressure cooker will have some pressure. And of course, the liquid will also have the same pressure at that high temperature. And because the above part is still almost an ideal gas, the pressure is dependent on density. So, pressure is dependent on temperature. So, temperature, if the temperature is fixed, the density of the liquid and the gas will be fixed as well. I want to identify those densities. How do I do that? This is standard thermodynamics. Pressure, this is the Amal's free energy, canonical and simple description. EPN, pressure, you can write in terms of temperature and density only. Temperature, number of particles, volume, or temperature and density only. So you get this to be density times their small f. Small f is the free energy density. So small f into V is your capital F. Okay. So we have this equation. Chemical potential is this equation. Just following the definitions of canonical. And we are discussing law, this common tangent law. So if you know small f is dependent on the system. Small f will be something for van der Waals gas, it will be something for a polymer solution, something else. It will be something else for a Kolkata solution. So it is different for different solutions, but small f is a function of temperature and density for a single component system. For a two-component system, very similar derivation will be there, but at this moment think only of single components. One type of molecules, one type of density. Okay. So if you require this is a common tangent law, as you know. So below the critical, this is above critical point, it can be shown. Above critical point, the free energy density as a function of density goes like this. So you have only one single phase which has the lowest free energy. But below critical point, the free energy profile, this is small f versus n. Free energy profile, you have to think like this, and it is possible to draw a common tangent. This common tangent is equivalent to this equation. And the common tangent should touch this free energy density profile at these 2 points, this NA and NB. So this is higher density, so this is N liquid and N gas will be our solutions for that. So I am trying to drive on the point, once you know small f, you are done. You can use this simple thermodynamics, this thermodynamics, no statistical method. For small f, you need statistical methods. This is thermodynamics. So using this thermodynamics, it is possible to find these two coexisting densities. Now what happens actually in the system? So what I have done, this part, I have expanded like this.
This part, but after Maxwellian correction.
After Maxwellian correction, yeah, it will come. Very nice. After Maxwellian correction, without Maxwellian correction, I have these isotherms. These isotherms are pressure versus density. Remember the isotherm for pressure versus density, this is ideal gas. This is proportional to temperature. Just P is equal to N cavity. But this is van der Waals gas, interacting gas. For an interacting gas or any other similar system, for the interacting gas, the isotherms, they will behave like this. Below the critical point, there are two. There is a maxima, there is a minima there, and it goes up like this. Empirically, people could see that this part of the equation of state is unphysical. People actually see coexistence of two fluids, right? One is the gas, low density, one is the liquid and high density. So Maxwell construction, as Mufizar said, that there is a Maxwell construction that can be done. There is a way to do the Maxwell construction. Nothing, because the pressures are equal. You have to make sure the chemical potentials are equal. That's one way. There are other ways too. You have P versus V diagram, the areas should be equal. Not for P versus N diagram. P versus small p. P versus 1 over N diagram, the areas should be equal. This can be derived from thermodynamics. Okay. So if your average density falls within this dome for a particular temperature, there will be coexistence. If you are outside this dome, it's either pure liquid, pure gas, you can have different, so this is the critical point, you can have critical pressure, critical temperature, the isotherm, critical density. And the vapor pressure, as we have discussed, at a particular temperature for this particular isotherm, take this one, this is the vapor pressure. Why you have drawn the Maxwell's line? Okay. And there can be first and second order transition. First order transition is obvious, but suppose you have a constant pressure experiment, you can hit this point, there can be a jump in the density. The gas, the entire gas will convert to liquid. There will be a jump in density. That will be a first order phase transition. There can be a second order phase transition. How? That is continuous transition. If you exactly have this critical density, and if you come down along this line, that means you are decreasing the temperature, keeping the volume fixed. You can choose a volume of a particular amount of material so that it is equal to the critical density. For water, I believe it's 0.22 gram per cc. Okay. If you choose that, you come here, you can see, then it will start to phase separate. but the density difference is starting continuously. There is no jump like this. There is no jump. If you come down the critical density, you will see first continuous for second order phase. So in the same system, it is possible to see second and first order phase transition. Well, I believe somewhere, I'll just stop with this slide, that was a very simple result. You can see the coexistence power critical for the system. And I just wanted to show you one example where people can work with polymer solutions, actually charged polymer solutions, for which you can get very similar phase dynamics. Exactly following the same procedure. Only that small f I have told you is different. So everything lies in that small f which has to be obtained from statistical mechanics. I believe, yeah.
Okay. Thank you very much. So, exciting.
Arindam, one question. That Muthu Kumar is that senior old Muthu?
Yeah, my postdoc advisor.
Oh, right.
So he was waiting last February.
He will be around 80 now.
No, Muthu Kumar is 73.
So, any comments from anyone?
So, liquid crystal depends only the shape of the molecule.
Shape of the molecule, if the shape is anisotropic, then there is a chance to have liquid crystal phases. As I have told you, with the right temperature, right density, the solvent has to be, supportive.
So, this is the only.
This is, yes, that's the most basic thing. If you have spherical molecules, ideal spherical molecules, you cannot have liquid crystal.
Anisotropy is very important.
Yeah, because which way it should crystallize, which way it should remain liquid, there is no asymmetry in the system to choose that. You need an asymmetry in the system to choose a particular direction. That is why.
So, when we see the nematics the phase transition, so if we think about the bacteria in a culture medium, so does the order when the temperature decreases, orders to the crystal media like that?
Order.
The bacteria in normal culture medium is disordered. But if we decrease the temperature, can we see the nematics, mectic, asymmetric seeds?
Bacteria?
Yes.
I don't know. I am not expert in bacteria. But if there is some nematic ordering in the system, then definitely symmetry goes down, and bacteria, they are not isotropic
No.
things.
They don't like shape.
But they are active matters, so it's a little bit complicated. But if you see in equilibrium some kind of a structure like nematic ordering, directional ordering, then it will be very similar. The physics will be very similar.
And we keep, if the anisotropic material we give charge, so plus charge or minus charge, there will be an additional attractive or repulsive potential.
Charge is very complicated because till now the intermolecular interaction we are talking about is short-range because it's van der Waals. It's like dipolar, right?
Yeah.
It's dipolar. Dipolar interaction or van der Waals interaction is termed as non-electrostatic interaction in condensed matter physics, which is not right because all interactions in condensed matter physics is electrostatic. What else can it be? Cannot be gravitational, strong and weak are not in our domain, so only can be electrostatic. Monopolar interactions, only monopolar interactions are considered as Coulombic interactions. Okay, and monopolar interactions are long-ranged, unlike van der Waals interactions, which is short-ranged. So it can be very difficult, very difficult.
1 over r square.
Yeah?
1 over r square.
1 over r square.
So, it seems that we have